What does it take to run an HVAC system for nearly 30 years and never have an emergency service call when most of your neighbors are on their second replacement? I've done it on my own house for 22 years. The trick isn't more maintenance, it's about removing strain. 28 years working out of a service van across Ohio, Pennsylvania, and now Texas, and the systems I see fail aren't the ones that get the least maintenance. They're the ones that run under constant strain. Electrical strain from grid surges and motor inrush current. Airflow strain from undersized returns and clogged filters. Thermal strain from condensers cooking in direct sun. Refrigerant strain from chronic mischarge. Cycling strain from oversized equipment short-cycling itself to death. The system on my own house has hit 22 years on the original compressor, not because I baby it, but because I removed the strain sources one at a time. I'll walk you through the 5 places strain hides, plus the things I deliberately do not do that most maintenance videos push on you. And stick around to the end because the single measurement I take twice a year tells me more about system health than every other check combined, and it costs $15 in tools. Let me start with the framing because it changes how you look at every piece of HVAC advice on the internet. Equipment does not fail because it gets old. Equipment fails because it gets strained. A capacitor doesn't slowly age out of spec on a wall calendar. It loses microfarads after each cycle, and the more strained the system is, the more cycles per day, the faster the capacitor dies. A compressor doesn't have a 15-year clock. It has roughly 100,000 starts in it, give or take. Strain the system into more cycles per day, more amps per cycle, and you burn through that allotment in 8 years. Reduce the strain, and the same compressor runs 25. You've probably seen this on your own block without putting words to it. Your neighbor with the loud, oversized unit that turns on and off every 15 minutes has replaced his compressor twice. The other neighbor with the boring single-stage system in the shade with proper ductwork is on year 20-something. Same brands, same climate, different strain profile. That's the whole video. Strain source number 1 is electrical. Most HVAC failures actually start at the electrical components, the capacitor, the contactor, the control board, and they fail because of strain that happened upstream. Surges from the grid, voltage sags during peak summer load, motor inrush current spiking on every compressor start. 3 things on my own system handle the electrical strain. First, a hardwired surge protector mounted at the outdoor disconnect. $80 to $100 for a quality unit from Intermatic or Dytech. Takes about 30 minutes to install if you know how to safely open a disconnect, more if you don't. Catches lightning-induced surges and grid switching transients that otherwise kill control boards and ECM motors. I'll admit I overlooked this for the first 10 years on my own system, until a summer storm fried the control board on the original air handler. That repair cost me $300 and a Saturday I'd rather have spent on the lake. The surge protector went in the following week. Second, a soft start kit on the outdoor unit. Newer than a hard start kit and gentler on the compressor. Soft start ramps the motor up over a half second instead of slamming it from 0 to full speed. Compressor inrush current drops by about 40 to 60%. Less strain on every start, every day for the life of the system. About $250 to $400 installed. Third, an annual lug torque check inside the disconnect box. Loose connections heat up under load, which causes more loosening, which causes arcing, which is how outdoor disconnect fires actually start. Pull the disconnect, open the box, verify the line side and load side lugs are tight. 2 minutes a year. Most homeowners never do it. That trio drops electrical strain to almost nothing. Most of the electrical components on my own system, the original capacitor included, are still functional at 22 years. Strain source number 2 is airflow. The compressor doesn't read airflow directly, but the blower motor, the evaporator coil, and the entire refrigerant cycle all suffer when air can't move through the system. The evaporator coil is the indoor coil where refrigerant absorbs heat from the air. Looks like a metal A-frame inside your air handler. When airflow drops, refrigerant absorbs less heat, suction pressure drops, and the compressor strains on every cycle. My own system runs a MERV8 pleated filter, deliberately on the low side, swapped every month during cooling season and every 2 months in winter. I covered this in the filter video, but the short version is that high MERV filters strangle the blower motor on most residential systems, and the strangling shows up downstream as a refrigerant problem or a coil freeze that the contractor mistakes for a charge issue. The return air ductwork in my house is sized at roughly 1 square inch per cubic feet per minute of system airflow. A 3-ton system moves about 1,200 cubic feet of air per minute, so the total return area needs to be about 1,200 square inches, which is one large return grill about the size of a typical doormat. Most older houses have half the return area they should. I rebuilt mine in year 5 to fix exactly that problem. Took a Saturday and about $100 in flex duct and a larger grill. Supply ductwork in my house is sealed with mastic at every joint and seam, not foil tape. Foil tape peels off in attic heat after a couple of years. Mastic stays put for the life of the system. Building Science Corporation has data on this if you want to go deep on it. That covers airflow strain. Blower motor on my unit is also still original. Strain source number 3 is thermal. The outdoor condenser unit's job is to dump heat from inside the house into the outdoor air. When the outdoor air is hot, the condenser fights every degree of that transfer. Put the unit in direct sun on a black asphalt pad in a 100-degree afternoon, and the surface temperature can hit 140 Fahrenheit, about the temperature of a fresh asphalt repair under your shoes. 3 thermal fixes on my own setup. First, a wood lattice shade structure on the south and west sides of the outdoor unit, set back 2 feet so airflow isn't restricted. My wife thought I was building a chicken coop. The shade drops surface temperature on the condenser by about 25 degrees on a hot Texas afternoon, which means the compressor pulls less amps to dump the same heat. Second, no grass or shrubs within 2 feet of the unit. Grass clippings get pulled into the coil and the coil gets dirty fast. Crushed gravel out to a 2-foot radius solves it permanently. Third, no other heat sources nearby. The unit is not next to the dryer vent, not next to the grill, not on the same wall as the kitchen exhaust. Heat sources stack up and you don't notice it until the cycle times stretch out. Phoenix climate magnifies all of this. A buddy who runs a shop out there told me his average customer's condenser surface temperature runs 10 to 15 degrees higher than mine on the same afternoon, and his average compressor replacement happens about 5 years sooner. Same brands, different thermal environment. The data lines up. Strain source number 4 is refrigerant. The refrigerant charge inside your system is supposed to stay at the exact mass specified on the manufacturer's data plate, off by 10% in either direction, and you're straining the compressor on every cycle. Off by 20%, and you're cutting compressor life in half. 2 things to know about refrigerant strain. First, you can't directly measure it yourself unless you're EPA 608 certified, which I am, and you have a manifold gauge set, which most homeowners don't and shouldn't. What you can demand from any tech who services your system is documented subcooling and superheat numbers in writing, recorded with the date and the outdoor temperature. Anything involving refrigerant repair requires EPA 608 by federal law, and that's the line where I stop and call a buddy even on my own equipment. Second, refrigerant strain often comes from suction line damage. The suction line is the larger of the 2 copper refrigerant lines running between your outdoor and indoor units, wrapped in foam insulation. When the foam UV degrades and falls off, the suction line absorbs heat it shouldn't, which raises superheat at the compressor, which strains it. Inspect your suction line insulation every spring. If you see bare copper anywhere, replace the foam with Armaflex pipe insulation, about $8 for a 6-foot section at any home. Center. Refrigerant work is one of the few HVAC areas where I deliberately defer. The system stays healthy because I don't let anyone touch the refrigerant unless the data shows it actually needs touching. If you're getting value out of this, hit subscribe. We've got more of these coming. Back to it. Strain source number 5 is cycling. Every time your compressor starts, it draws a brief inrush current that can be 5 to 7 times the running current. That's the strain spike. Reduce the number of starts per day, you reduce total lifetime strain on the compressor. A typical residential compressor is rated for somewhere in the range of 100,000 starts over its service life. At 10 starts per day, average for an oversized system, that's about 27 years of starts. At 6 starts per day, average for a properly sized system, that's 45 years. Same compressor, different cycling load. 2 things on my system reduce cycling. First, the system is properly sized through a manual J-load calculation, not through a contractor rule of thumb. Most residential systems are oversized by 20 to 30% because contractors overquote tonnage to avoid callbacks. An oversized system reaches set point fast, then shuts off, then turns back on a few minutes later. More cycles per day, more strain per year, shorter compressor life. A properly sized system runs longer cycles, fewer per day, and lasts longer. Before anyone says it in the comments, yes, I know the common belief is that a bigger AC cools the house faster, and that's a good thing. It cools the air faster, but it doesn't pull humidity out because the runtime is too short for moisture removal. You end up with a cool, clammy house and a dying compressor. Second, my thermostat differential is set wider than the factory default. Default is usually 0.5 degrees. Mine is set to 1 degree, which is about the difference between you noticing the temperature and you not noticing. That cuts cycle frequency by roughly 30% in shoulder seasons. Some thermostats let you adjust this in the installer menu. Worth digging into. My wife runs ours at 68 in summer. I run it at 76. We've been negotiating that for 28 years, and the differential setting is the one thing we agree on. Now for what I deliberately don't do. This is the part of the video that gets me arguments in the comments. I don't deep clean my blower wheel every year. If it's running quiet and the temperature split is in range, I leave it alone. I've talked to too many techs who threw a wheel off balance by aggressive cleaning and created a vibration problem that wasn't there before. I don't run my filter at MERV 13 or higher. The air filter industry will tell you that you need the highest MERV available for indoor air quality. The HVAC engineering will tell you that higher MERV strains your blower. I pick the side that keeps my equipment alive. I don't pay for a maintenance service contract. 22 years of running my own preventive routine has cost less than 2 years of a service contract. I don't add UV lights, electrostatic filters, or any of the bolt-on air quality products contractors push during a service call. None of them solve a strain problem. Most of them add one. I don't replace components on a calendar schedule. Some maintenance content tells you to swap the capacitor every 5 years regardless of condition. That's silly. I swap parts when the readings drift, not when the calendar rolls over. The temperature split and the multimeter tell me when to act. And I don't crank the thermostat down on the hottest day of the year. The compressor only has one speed. Setting it to 68 doesn't make the system work faster. It just makes it run longer past the comfortable point. Set point is a destination, not a throttle. The toolbox for all of this is almost embarrassingly small. A $15 digital multimeter that reads voltage, resistance, and microfarads. A $15 infrared thermometer with a laser pointer, the kind you can find at any home center. A basic screwdriver set with Phillips and flathead in 3 sizes. A roll of masking tape for labeling wires before I disconnect anything. That's it. Total cost under $50. Most homeowners think HVAC diagnostics require a $5,000 pro kit. Manifold gauges, micron gauges, refrigerant scales, leak detectors. They don't, unless you're getting into refrigerant work, which I'm not on my own system. Unless I have to. For everything except refrigerant, the multimeter and the infrared thermometer cover 90% of the diagnostic ground. The line where I stop and call somebody else, even on my own equipment, comes down to one word: reversibility. If I make a change and it doesn't work, can I easily undo it? If yes, I'll try it myself. If no, I call. Gas valve work, irreversible if you crack the manifold. I call. Refrigerant cuts, irreversible once you've released the charge to atmosphere. I call. Drain line cuts, irreversible until you repipe. I call. Anything inside the burner compartment past a visual inspection, irreversible and dangerous if you misalign something. I call. Cheap electrical components and visual checks, reversible. Pull a wire, label it with the masking tape, swap a part, test it. If it doesn't work, put the old one back. That's where I do my own work. And the single measurement I take twice a year that tells me more than every other check combined. The temperature split across the indoor evaporator coil. A healthy residential air conditioning system, properly sized, properly charged, with clean coils and good airflow, produces a temperature drop of 16 to 22 degrees Fahrenheit between the return air and the supply air. Return air comes back to the system warm from the house. Supply air leaves the system cool, after passing across the evaporator coil. The difference between those two temperatures is the temperature split, and it tells you whether the cooling is actually happening at the rate it should. The procedure is simple. Run the system in cooling mode for 15 minutes. Actually, in 100-degree weather, make it 20, so the readings stabilize. With a $15 infrared thermometer, take the temperature at a return air grill away from any supply registers. Then take the temperature at a supply register, ideally one of the central registers, not the farthest one from the air handler. Subtract supply from return. That's your temperature split. 16 to 22 degrees, the system is healthy. Below 14 degrees, you have either low refrigerant, dirty coil, restricted airflow, or a charge problem brewing. Above 24 degrees, you're under airflow or overcharged. Either drift is a warning. I take this reading every spring after a 15-minute warm-up. I take it again in the middle of summer on a hot afternoon, just to verify. Wrote my baseline number on a sticky note inside the air handler cabinet years ago. Each spring I compare. Year 15 on my system, the split was 21 degrees. Year 16, 20. Year 17, 18. Year 18, 16 and dropping. That's when I knew something was changing. Pulled the indoor coil, found heavy dust between the fins, cleaned it carefully with a coil brush, ran the test again. 21 degrees, back to baseline. The system was telling me what was happening. I just needed the discipline to listen to the number. Year 21, the split came back at 24 degrees on a spring reading. Higher than baseline by 3 degrees. That direction usually means overcharge or airflow restriction. Check the filter, was due for a swap anyway. Fresh filter went in, ran the test the following morning. 21 degrees, back to baseline. Did not need a tech, did not need a service call, did not need to second guess. The number told me. Think about that. A $15 tool, 2 readings a year, and the system tells you what's wrong before any contractor would catch it. That's the whole secret. Not a notebook, not a maintenance schedule, not a service contract. One measurement twice a year with a tool that costs less than a single weekend service call. The temperature split is the dashboard light most homeowners never look at. 22 years on the original compressor isn't an accident, and it isn't bragging. It's the math of strain accumulated over time. Reduce the strain, reduce the wear, extend the life. The 5 strain sources I covered, electrical, airflow, thermal, refrigerant, cycling, each one adds up over decades. Address all 5 and your equipment stops failing the way most equipment fails. Address none of them and your system runs the same race every overworked, oversized, sun-baked, overfiltered unit in your neighborhood is running. The race ends with a contractor in your driveway quoting $9,000. The equipment doesn't have to fail. It mostly fails because we let it.